Hi there everyone, this is Ms. Page. I am glad you are here. In this lesson we are going to talk about how to simplify trigonometric expressions. So an expression doesn't have an equal side, doesn't have a left or a right. We do use identities to simplify expressions, and we'll talk about some of the rules about how we identify if an expression is in its simplest form for trigonometry. Here in our prior knowledge we have learned some identities already. We know that secant and cosine are reciprocals, so we know here that secant can be written as 1 over cosine. We also then know that cosine of theta could be written as 1 over secant theta. Here we see that cosecant is 1 over sine, which also means sine of theta is 1 over cosecant of theta. Here we see that cotangent as a quotient identity is cosine over sine. We also know that cotangent and tangent are reciprocal of one another. So we have this identity that tangent is 1 over cotangent, as well as the fact that we have a quotient identity for tangent of sine over cosine. We will be using all of those at different points in simplifying trig expressions. We are also going to introduce another identity, a very important identity that is based on the Pythagorean theorem, because remember that within the unit circle we've constructed the unit circle so that these triangles would be our special right triangles. So the Pythagorean theorem, which works for right triangles, applies, and we know that the unit circle has a radius of 1 unit, which is the hypotenuse of that little right triangle there. We know that this portion right here, which is the x coordinate, and the length of that line segment is equal to the cosine of the angle here of theta. And we know that this side is our y value, creating our points, and that y is the sine of angle theta. So that means that if we look at it, you can here it's shown as y squared plus x squared equals 1 squared. That's our Pythagorean theorem, starting here, squaring, and 1 squared. You can also do x squared plus y squared equals 1 squared, but the identity is generally written with sine first, so that's why it's written this way in this explanation. So y is our sine, and so we get sine squared. I want you to make special note of how we write sine theta squared, and here we can, this is actually read sine squared theta, but it means sine of theta times sine of theta. So when we see this here, it means sine theta times sine theta. And then x is cosine, so we get cosine theta squared, which is written cosine squared theta. And that means cosine theta times cosine theta. And then 1 squared, of course, is still 1. So sine squared plus cosine squared equals 1 is what we call a Pythagorean identity. And it is super important. So make sure that you highlight it, star it. It's on the next page too, but this is a biggie. All right, so here what we're going to do is look at how we derive some other Pythagorean identities from our initial Pythagorean identity of sine squared plus cosine squared equals 1. So we start with our Pythagorean theorem identity, sine squared plus cosine squared equals 1. If we divide both sides by sine squared theta, this is what it creates. Anything divided by itself is 1. Cosine squared over sine squared, well, we have a quotient identity that says cosine over sine is cotangent, so cosine squared over sine squared, because the exponents match, will be cotangent squared of angle theta. And then 1 over sine and cosecant are reciprocals, so 1 over sine squared becomes the reciprocal squared. So we get cosecant squared. So we have 1 plus cotangent squared theta equals cosecant squared theta. If we take our Pythagorean identity, sine squared plus cosine squared equals 1, and divide both sides by cosine squared theta, it creates this. Sine squared over cosine squared will become tangent squared. Cosine squared divided by itself becomes 1. and then 1 over cosine squared. Cosine and secant are reciprocals of each other, so this becomes secant squared of angle theta. All right, we're going to talk about now some alternate forms of our 3 Pythagorean identities. So here we have our main one, and we create alternate forms by using our basic algebra. If we subtract cosine squared from both sides, it creates sine squared theta equals 1 minus cosine squared theta. If we subtract sine squared from both sides, it creates cosine squared equals 1 minus sine squared theta. These are worth putting in some effort to memorize right here, along with, of course, your first one. They do show up. If you don't have them memorized, then it just requires more work in certain problems. You can get to the end in most cases, I would say, but definitely does go faster when you know the alternate forms. For our alternate forms of our 1 plus cotangent squared equals cosecant squared, we could subtract 1, which would give us cotangent squared theta equals cosecant squared theta minus 1. Or we could subtract the cotangent squared from both sides. In that case, it's that form is usually written cosecant squared theta minus cotangent squared theta equals 1. For our tangent squared plus 1 equals secant squared, again, similar algebra, we could subtract 1 from both sides, which gives us tangent squared theta equals secant squared theta minus 1. We could also subtract the tangent squared theta, and that form is usually written secant squared theta minus tangent squared theta equals 1. All right, so now here these are our reciprocal and quotient identities that we've been using for a while now. They're just here for reference. Here is kind of a outline of some of the strategies that can be used for simplifying trigonometric expressions. So you do substitutions using your identities. Could be quotient identities, reciprocal identities, or Pythagorean identities. Sometimes you can try factoring. We'll look at some problems where we focus on factoring. To remove parentheses, you can look at using your distributive property. If you have ratios in which you have to add or subtract those ratios, you can look at getting a common denominator and then adding like you would fractions with a common denominator. If you want to change, and this actually is often how we get a common denominator, is we multiply by a ratio of 1, so these two kind of go together in many cases. And then if everything else fails, and you've got tangents and cotangents and secants and cosecants, a strategy that sometimes will work is to rewrite those other 4 in using the reciprocal and quotient identities in terms of sine and cosine. So these are some of the rules for how we know that we are actually done with a simplifying problem. So recognizing a simplified trigonometric expression here. So if it ends up being in terms of a single trig function, like it's a power of sine, a power of cosine, a power of tangent, and so on and so forth, that's considered simplified. The expression does not involve any fraction forms. For example, if you end up with sine theta over cosine theta, you can't leave it like that. You have to say that's equal to tangent of theta before it's considered simplified. And that's kind of going along with this. No more identities can be used to further simplify the expression, which is kind of an overall general way of looking at things. All right, let's take a look at some problems. So at any time, if you want to try any of these problems on your own, pause the video, give them a try, and then come back to the video and see if you come to the same conclusion I'm going to come to. Because there are not in this particular lesson any practice problems for these simplifying problems. All right, and I think we have 4 examples. So after the first one, you might want to try one on your own. All right, so when I look at this expression here, what I see is that Both terms involve a factor of sine x. And I think, oh, okay, well, I've got a common factor. Now, I'll be quite honest with you, with complex problems of these types, sometimes you can start with something that you think will work, and then, well, it ends up taking you someplace that is just a mess. And so you go, never mind, let me try something else. That does happen. With the simpler ones, usually you can get there with multiple starting places. But here's one. I noticed that, okay, I've got a common factor of sine x. So just like I would factor out a common factor of 2, I can factor out sine of x. And so sine of x times cosine squared x is sine x cosine squared x, and sine x times 1 is sine x, so this becomes minus 1. Now, we have an identity, part of our Pythagorean identities, and all our alternate forms. So we know we have sine squared x plus cosine squared x equals 1. And yes, I know I just changed theta to x. Theta is an angle measure. Sometimes we use x to represent the angle, so that part can be anything it wants to be as long as it's the same. If I subtract cosine x, what I get is sine squared x equals 1 minus cosine squared x, remember. The problem with that is this is 1 minus cosine squared, and this is cosine squared minus 1. But I go, oh, those are opposites of each other. So instead of factoring out a sine x, I can factor out a negative sine x, or a negative 1 times sine x. Anything times negative 1 would have, well, if I factor out a negative 1, it changes the sign. So that's going to make cosine become negative. So negative 1 times negative cosine is my cosine, or times cosine squared is my cosine squared. And negative 1 times positive 1 is my negative 1. And then if I rewrite this order, that's the same thing as 1 minus cosine squared x. So this is what I have now. And now I can use this Pythagorean identity, and for 1 minus cosine squared x, I can substitute what it's equal to, which is sine squared x. So this becomes sine squared x times this negative sine of x. Now, one of the other things is that when we're multiplying trig functions together like this, it's just like multiplying powers of a variable or a number. So we know that if we take x times x squared, that's x cubed. But our powers are actually on sine in this structure, not on x. So we have a 1 plus a 2, and that gives us negative sine cubed x. This is now in terms of a single trig function. It's a power of sine. And then it has a coefficient of negative 1, and that's fine. Nothing you can do to change that. So this would be considered the simplified form of what we started with. So this is equal to negative sine cubed x in its simplest form. All right, let's look at another one. So here's the expression that we are going to simplify. So again, what I go looking for things that I'm familiar with, and again, I've done a lot of these problems. You're just starting out, so I will recognize certain things more quickly than you will in many cases, and that's normal. That's why I'm sharing with you the things that I do look for. So here I notice, okay, I've got a cosecant x as a common factor between these two terms. So I'm going to see what happens if I factor out cosecant x. And I notice, oh, I'm getting this cosine squared x minus 1 again. So let's change it to factoring out negative cosecant of x. And then that's going to change my negative 1 to a positive 1, and my cosine squared to a negative cosine squared. Then I can use, again, that Pythagorean identity, that alternate form, that sine squared x equals 1 minus cosine squared x. And so this will become sine squared x. Now what I have is negative cosecant x times sine squared x. And here's where being familiar with your identities, comfortable with them, which requires practice, is helpful, because now I go, oh, okay, well, I know that cosecant and sine are reciprocals of each other. So you can actually do it one of two ways. So let's look at it this way. I could take cosecant and write it as 1 over sine of x. So that would become negative 1 over sine of x times sine squared x over 1. And then what I'm looking at is this would be like reducing power. So I know that x squared over x, that would be, I'd subtract those exponents, and that would be just x. But again, the exponents are on the sign. So 2 minus 1 is 1, and that gives me then negative sine x as my simplified form. Now, there is another way it could go. It's a little longer, and we come up with exactly the same answer. So let me show you that, though. If I can get this. I'll take this out of the way. All right. So we could also leave negative cosecant of x with a denominator of 1 and write sine squared is 1 over cosecant squared x. This reduction, though, puts a cosecant in the denominator. And if you recall, one of the things about our simplest form, going back here, is that there should not be any fraction forms in a simplified answer. And we've got a fraction form that then we would have to realize, oh, well, cosecant and sine are reciprocals of each other, so that would then become the reciprocal, which would be a negative sine x. So either way, it works its way to negative sine x. All right, let's take a look at another one. So with this problem, we have a situation where we don't have that nice common factor anymore. So we are looking at that strategy not working for us. So here, what I'm looking at is I have sine and cosine. Not much we can ever do with those unless we have sine squared or cosine squared. But a sine and a cosine to the first power, nah, we're kind of stuck. Cotangent, however, we can use a quotient identity on that. We know that cotangent is cosine over sine. And that would then be times this cosine x here, which has a denominator of 1. And so cosine times cosine would give me cosine squared. Now this sine x has a denominator of 1. And so what we have here is basically like the sine of x acts like a whole number, and the cosine squared over sine is like a fraction. So we need a common denominator to combine these into a single expression. And so the lowest common denominator would be 1 times sine x, which is just sine x. So I'd have to multiply by a ratio of 1 over here of sine x over sine x. Sine times sine would be sine squared, so this becomes sine squared x over sine x. And then we have this plus cosine squared x over sine x. So just like when we are adding fractions, now that we have a common denominator, we will add the numerators, and our denominator will be that common denominator of sine x. And so we get sine squared x plus cosine squared x. At this point, we have to realize we have a Pythagorean identity that involves sine squared plus cosine squared. And it says that sine squared x plus cosine squared x equals 1. So that means that we can substitute sine squared plus cosine squared for 1. So we get 1 over sine of x. Again, remember, we can't stop here because one of the rules about simplifying is we should have no fractional forms at all, and sine and cosecant are reciprocals of each other. So this becomes cosecant of x, like so. Notice I've never used any equal signs in these problems. That's actually inappropriate because we're not working with equations that do have equal signs. We're working with expressions. So you'll notice it's like a vertical progression of just from one step to the next. This is what it is now, then this is what it is, then this is what it is, then it goes to this, then it goes to this, and then finally it ends up at that. Try to match and practice that format, please. All right, let's see what we've got next here. All right, this is another example of simplifying. So here we again have that issue where we do not have the common factor. We do have a cosecant and we have a cotangent. Cotangent again is cosine over sine. And cosecant and sine are reciprocals of each other. So sometimes you might recognize what to do with two parts that can lead you towards being able to simplify. Sometimes you won't. You have to try something and then you realize, oh, okay, now I need to do this with that other part and stuff. But because this would be, I'm going to do the second part first. So cotangent is cosine over sine. So this gives me cosine times cosine over sine. So I get cosine squared x over sine x. And cosecant is the reciprocal of sine. So that is 1 over sine x. So that then gives me a common denominator without having to do that ratio of 1 like I had to do in the previous problem. So now I have 1 minus cosine squared x over the common denominator of sine x. And I have an alternate form of the Pythagorean identity. Remember that if sine squared plus cosine squared equals 1, then sine squared is equal to 1 minus cosine squared. And so again, this part right here is equivalent to sine squared x. So I now have sine squared x over sine x. And this is a ratio of powers of sine. So just like reducing x squared over x gives me x, sine squared over sine will give me sine of x, like so. All right, so let's take a look at what else is in this lesson. So another thing, we're just going to practice factoring by itself right now. We will eventually use it. Actually, I think we use it in the next lesson, and we'll also use it in future lessons to help us solve. And we sometimes use it to help us simplify expressions, reduce common factors, things like that. But right now, we're just going to practice the factoring by itself. One of the things we have to become comfortable with is seeing an expression like this as a difference of two squares. So this is secant theta quantity squared minus 1 quantity squared. And any difference of squares will factor into two binomials that are conjugates of each other. So we'd have a secant theta and a secant theta. We'd have a plus 1 and a minus 1. And there's our factored form. Let's look at another one. Here we have a trinomial structure. And our trinomial structure here involves powers of tangent and a constant term. So I'd be thinking, okay, well, no common factor, GCF between all three. Sometimes there might be. But my trinomial is actually a quadratic structure. Like we normally have like a 4x squared plus an x minus 3. So this we would try to factor this into binomials using factors of the 4x squared and the negative 3. So what we do here, we would split that into either a 4x and an x, or maybe a 2x and a 2x, depending on what we thought was going to work. And the same thing is true for 4 tangent squared. We would look at this as two binomials, and we could try 4 tangent theta and 1 tangent theta, or we could try 2 tangent theta and 2 tangent theta. I think this is the one that's going to work though. If I put a 3 here and a 1 here, and I make this a plus and this a minus, checking it, always check, remember. So 4 tangent times tangent, that would be the 4 tangent squared. Then 4 tangent times 1 gives me a plus 4 tangent. Negative 3 times tangent gives me a negative 3 tangent. And negative 3 times 1 gives me a negative 3. And 4 minus 3 is 1, so that gives me plus 1 tangent theta. So I get all three terms checking. So that means that my factored form of this is 4 tangent theta minus 3 times tangent theta plus 1, like so. All right, I think there is a practice problem now. Yep, so you should pause your video here, try to factor this, and then turn your video back on, and we'll see if you got it right. All right, let's take a look here at the answer. So hopefully you saw this is a difference of two squares, and it factors into those binomial factors. Again, always a good idea to check and make sure that, especially with this new format with involving trig functions, that things are working out. Here's another practice problem. Pause your video. So here's the factored form. So we have that trinomial, that quadratic structure, and factors of 2 cosecant squared or 2 cosecant theta and cosecant theta, and the factors of positive 6 that work are a negative 3 and a negative 2. That gives us a negative 3 cosecant plus a negative 4 cosecant, which is our negative 7 cosecant theta. All right, here's another practice problem. Pause your video. Let's take a look at the factored form. So this one is a binomial structure with a GCF. Not only does it have a GCF of 3 because of the 6 and the 3, it also has a power of sine theta that is part of the GCF. So we have 3 sine theta as our GCF, and then that would be times 2 sine theta. That's our 6 sine squared theta. And then 3 sine theta times a negative 1 gives us the negative 3 sine theta. All right, let's move on from here now. So let's take a look at factoring an expression like this one. This one is a little different, and we have to recognize that difference. The difference that I'm speaking to is that here we have a power of cosecant, and in the middle we have a power of cotangent. This is not going to factor into two binomials the way that we saw the previous problems doing. What we have to do here in this type of problem is use an identity so that we can get powers of either both cotangents or both cosecants. And because we are looking at a cosecant squared, I would go to a Pythagorean identity and see if there was anything here that would help me. And there actually is. There is a Pythagorean identity that says 1 plus cotangent squared theta equals cosecant squared theta. And I have a cosecant squared theta, and this involves cotangent. So it allows me to do a rewrite of, or a substitution for this, and then I'll have powers of cotangent and then just constants. So this would become 1 plus cotangent squared theta, and then we have this part, minus cotangent, well, actually, sorry, no theta. Let's make it all x's like it's supposed to be. So let me go back. Cotangent x minus 3. So putting this into standard form, I'd have my positive cotangent squared x minus cotangent x, and then I have a 1 and a negative 3, which gives me negative 2. This is a quadratic structure because now I have cotangent squared and cotangent to the first. So now I can look at factoring this into two binomials. The factors of cotangent squared would be cotangent and cotangent. And then the factors of negative 2 that are going to help me get that negative 1 are going to be a negative 2 and a positive 1. That's going to give me, like I said, cotangent squared. This is negative 2 cotangent plus 1 cotangent, which is a negative cotangent. And so this would be my factored form. All right, there's a practice problem here for you to try. Pause the video, see if you can figure this one out. All right, let's see how you did. So here we have a Pythagorean identity that involves secant squared, and it says that secant squared is equal to 1 plus tangent squared. So we can do a substitution for that. Now we have all powers of tangent and then just numbers. Put it into standard form, we then have tangent squared plus 3 tangent plus 2. And then that will factor into this product of binomials. All right, one other thing I believe for us to talk about in this lesson, and that we have previously learned in prior knowledge that to add fractions with different denominators that we need a common denominator first. And so the lowest common denominator here would be x squared, being x times x here. They have a common factor of x and then one factor of x that's not common. So we'd have x times x, or x squared, as the lowest common denominator. multiply by a ratio of 1 to create that x squared in both, and then we can combine them all over x squared. So we're actually going to use that same strategy in this next problem, but it's going to involve our trig functions. So here what we're looking at is we want to add together, perform this addition, and then simplify as much as possible, combining like terms and so on and so forth. And we have different denominators. So how do we go about getting this? So some people mistakenly think that, oh, well, I need to multiply this one times 1 plus cosine theta over 1 plus cosine theta, and this one times sine theta over sine theta. That'll give you a common denominator, but it's not going to get you to the simplest form. What we need to be more sophisticated here. We need to realize that we have, if we go back to the idea of our Pythagorean identity, that we have sine squared equals 1 minus cosine squared. 1 minus cosine squared is a difference of two squares, and that factors into 1 plus cosine and 1 minus cosine. And we have a 1 plus cosine. So we can actually create sine squared theta by using a ratio of 1 made out of 1 minus cosine theta. So we would actually take this and multiply 1 minus cosine theta over 1 minus cosine theta. And this is going to give, I'm going to have to distribute this. I'm going to get sine theta minus sine theta cosine theta over, this is going to give me, so multiplying 1 minus cosine theta times 1 plus cosine theta gives me 1 minus cosine squared theta. 1 minus cosine squared theta is sine squared theta. So now what I have so far, with just the expression here on the left side, is this. Now, this one has a denominator of sine, and I need a sine to match this sine squared I just created. So over here, I'm going to use a ratio of 1 sine theta over sine theta. And that's going to become plus cosine theta sine theta over sine theta times sine theta. And that is my sine squared theta. Cosine times sine is the same thing as sine times cosine. And I flip it around because here I've got a negative sine theta cosine theta plus a positive sine theta cosine theta. They're going to add together and give me 0. Anything plus its opposite is 0. So this now becomes sine theta over sine squared theta, the common denominator. Powers of sine will reduce to 1 over sine theta. Remember that in simplified form, we can't have fractions like this. Sine and cosecant are reciprocals, so should not have used an equal sign. I can use like an arrow or something like that. That's okay, but I shouldn't use equals. This would be cosecant of theta. And that's now done and simplified. So we added and we got it into simplest form. All right, there's a practice problem next. You should pause, give this one a try, see how you do. All right, let's take a look at the result here. So in this one, we're going to need to, these are 1 plus sine theta and 1 minus sine theta are conjugates of each other. So if, in this case, I would multiply the one on the left by 1 minus sine theta over itself, and the one on the right by 1 plus sine theta over itself, because that's going to give me 1 minus sine squared theta in my denominator on both of them. And then adding my numerators, 1 plus 1 gives me 2. And negative sine theta and positive sine theta add up to 0. Also, 1 minus sine squared theta is equal to cosine squared theta. And so that gets simplified. So now I've got 2 over cosine theta. Cosine is the reciprocal of secant. So these guys pull to the top as the reciprocal of secant. And that's shown here, breaking it down a little bit more. And that 2 just stays a 2 as a multiplying factor. We end up with 2 secant squared theta. All right, that's all of the problems that are in this lesson. And you can now give your assignment a try. Have a good day.